Welcome to Chapter 8, Day 11. We're going to talk about functions with more than one independent variable. We're going to have two problems today in the notes. These two problems are very different, so we want to make sure we specify how they are different and then use them as resources moving forward. So, for example 1, this is page 444 called the beam strength model. The safe load for a horizontal beam, such as those that hold up the floor in a house, very important, varies directly, okay, I'm going to highlight, directly as the width, directly as the square of the depth, and inversely as the length between the supports. This is going to be one equation. They are all directly inversely related to the same constant because it's one big sentence, one big problem here. Part A, we're going to write an equation expressing the safe load in terms of those independent variables. Then you'll see we're going to plug in if we have a 2-inch by 8-inch beam, 16 feet long, turned on edge so that its width is 2 inches and its depth is 8 inches, can support a load of 1,000. That information is going to help us create our particular equation, right? It gives us values so we can solve for the constant. Now, before we do any of that, let's start with our variables. As always, we have, let's go W maybe is width. That's in inches. We have D maybe for depth. That is also in inches. We have length. I'm going to do a little fancy L is length. That is in feet. And then I'm going to do a nice big L representing the safe load or how much it can hold. And that will be in pounds. Feel free to use whatever variables you want as long as you tell us. Reading the problem again, it says our safe load varies directly with the width. So K times the width, our constant multiplied by our width, directly as the square of the depth, so that's another multiply, and then inverse, which means division, by the length. One big equation with all three of those variables. Using the information it gives us, let's solve for the particular equation. It tells us you can support a load of 1,000. It's going to go right here. Our goal is to solve for K. It says our width is going to be 2. Depth, oops, I'm going to use a different color, sorry. Width is 2. Depth is 8. Make sure we do 8 squared. The depth is squared. All over the length it gives us is 16. So all the values I plugged in are in green. When you solve this, you'll find you'll have 1,000 equals 2 times 8 squared, which is 64, so 128K over 16. In the end, giving us K equals 125. That gives us our constant, which allows us then to look at our equation, substitute in our constant, and leave all our other variables intact. And that right there is your equation of safe load. Directly with the width, directly with the depth squared, and inversely with the length. Now part B says if the beam in part A is laid flat. So far we have two differences. It's either on edge, which looks like this right here. This is option A. Or it's laid flat, which is right here, option B. If the beam is laid flat, the width is 8 inches and the depth is 2. How many pounds can it support? Notice what changes, the depth and the width just flip. So we're going to use the same equation. L equals 125. This time our width and our depth are changing. I'm going to leave everything else the same. We still know it's 16 feet long, but this time the 8 is the width and 2 is the depth. So the 2 is being squared this time versus the 8 from part A. Typing this in your calculator, you get the load can support 250 pounds. So just from changing it from laying on edge to flat, it goes from supporting 1,000 pounds to only supporting 250. Which brings us to part C, which says, why are houses built with the floor beams as in part A, then part B? Well, it's obvious. It supports so much more. If it's on edge, like the picture part A, it's going to support 1,000 pounds. Versus if it's flat, it's only going to support 250 pounds. So, I'm going to write the beams support more weight when it's on edge, which is a pretty cool fact. So your house is hopefully built with the beams on edge. Part D, what is the safe load for the beam? 8 inches wide, 12 inches deep, and 12 feet long. Well, let's take our equation and just plug in those new values. So L is going to equal, we know our 125, our width, our depth squared over our length. Okay, our width is 8, depth is 12, which is being squared, and 12 feet long. Just type it in your calculator. You'll see that it's 12,000 pounds. So that holds a lot. That's really important. We want it to hold as much as possible if it's your house. Part E. A lot of people have trouble with part E because they don't look at the equation. So what I'm going to do is actually copy and paste the equation from above, and we're going to look at it. Okay. First part here. If the width is doubled, what will happen to the safe load? Okay, by what factor will it change? So if we double this width, so if I multiply this side by 2, this W is multiplied by 2, well, it means that the other side is going to be multiplied by 2. Right? It's going to have the same effect. So the safe load will also be doubled. What if the depth is doubled? Remember, the depth is already raised to the second power. So if I double the depth, it's going to be 2 to the second power, which 2 to the second is 4. So I just multiply this by the 4th. That means this will have to be times 4 to the 4th, multiplied by 4, I'm sorry. So you're just going to write, it will be 4 times the safe load, right? You'll multiply it by 4 because it's the depth squared. What about if the length is doubled? Notice the length is in the denominator. You're dividing. If the right side is divided by a factor of 2, well, the left side will be divided by a factor of 2. Or you can say it will become half. It's cut in half. The right side is cut in half. The left side will be cut in half. Please just look at your equation and maybe even try plugging in a value if you want to really see what happens to the right and left side. You have to look at the placement. Is it in the numerator or denominator? And is there any power associated with that variable? This is one example, my dears. One example where they all relate to the same equation. One big equation, same constant. Which leads us perfectly into a problem like number 8, the airplane flight speed model. This one, we'll notice as we read, is going to give us many little equations that don't relate to each other. Let's see. So the weight of the airplanes of similar shape are directly proportional, directly proportional to the cube of their lengths, period. In order for the airplane to fly, its weight must be directly proportional to the product of the wing area and the flight speed. period. The wing area varies directly as the shape of the length of the airplane. 3 different sentences, 3 different equations then. They don't have the same constant. They do not all relate, like the problem above, to safe load. One is weight, one is wing area, etc., etc. So let's first start off, as always, with our variables. I'm going to have W be the weight of the plane. I'm going to have my fancy L be the length of the plane. I'm going to have A be our surface area of the wing. And S can be our speed. Again, you pick your variables, it does not matter. Let's look at the first sentence. The weight of the airplane of similar shape are directly, so multiply, proportional to the cube of their length. So the weight of the plane directly proportional, so it's multiplied, by the cube of the length. So length cubed. Next sentence. In order for the airplane to fly, the weight, okay, so this one actually is going to be another weight, directly proportional, so multiply, to the product of the wing area, so I'll call that A, and the flight speed, that's S. We have to be careful. Those K values are different. So what's helpful to me is I like to write it as K subscript 1, K subscript 2, and we'll see in our next equation, which is area directly proportional to the square of the length. I'm going to call that K3. They are different constants. We want to keep that separate because when we combine these or when we use them to find other values, we have to make sure we keep them consistent. This is a very different setup than the first one. This one we have 3 equations and a ton of unknowns. There's nothing else we can do, which is extremely different than the first example. We'll go to part B and see if it starts to make a little more sense. So part B, from these equations, notice they're hinting that there should be more than one equation. Derive another equation. Fabulous. Expressing the speed, so we want speed of the airplane in terms of its length. So something in terms of its length. This is our goal. Okay, this is what we're shooting for. Speed in terms of length. Let's look at our 3 equations. Is there anywhere that we can start with S on one side, L on the other? Well, I do notice there's an L and an S. Oh, and they happen to equal the same variable. That could help me. That could be my start to get L on one side and S on the other. This is a puzzle. It does not matter if you go the same pattern as me. You can find it in a different way. But we're going to start with setting W equal to W. So that means setting the first equation, K1 times L cubed, equal to the second equation, which is K2 times A times S. The reason why I did that is because one side has L, one side has S. Well, the whole goal is getting S by itself, so I'm going to do a little maneuvering. I'm going to divide by K subscript 2A on both sides, which is going to leave me, I'm just going to rearrange the sides. S equals K1 L cubed over K2A. So we're getting there. We're pretty close. We have S in terms of L and A, though. This needs to go. I can't have area in part of this equation. All I want is other one is speed in terms of length. So this A has to go. Well, looking at the equations above, notice A is equal to K subscript 3 L squared. That's perfect. If I take that and substitute it in, I won't have the A anymore. All I have left on the right side is my length, my L. So look at that. Puzzle's coming into play. So I'm going to rewrite this. K1 L cubed over K2 instead of A. I'm going to put the K subscript 3, my constant, third one, times L squared. Which is great. I now have just S in terms of L. Yes, I have all those constants, which we'll talk about in a second, but this is what we need. If I just look at L cubed and L squared right here, exponent rules. When you divide like bases, you subtract exponents. So I can just write this as L. L cubed divided by L squared is just L. And we're going to call this K4, my fourth constant. And you're like, what? I have 3 already. I'm going to combine to a fourth. Well, yes, because you can't have all those crazy constants in there. It's going to confuse if it's inverse or direct. So this one is going to be S equals K subscript 4 times L. And you need to write a little note. What is K4? K4 is constant 1 divided by constant 2 times constant 3. All you did is took this right here and replaced it with K4. You do that so that you can see how is it related. Right? It has one big constant. So this would be your final answer. K is replaced with all of this. Your speed is now in terms of your length. You only have 2 variables with 1 constant. You need this in your answer. Otherwise, you won't get full points because we don't know what K subscript 4 is. Now it's pretty clear to look at this. How does the flight speed vary with the plane length? Speed vary with the length? Well, it's being multiplied. Multiply means directly. Directly variation. So it's directly variated. Directly variated with. Yeah, sure, let's go with that. So now we have to look at our equation again from the beginning. How much faster would the plane fly if you doubled its length? Right here. If you doubled this length, so timesed it by 2, what would happen to the speed? Times this side by 2, the left side would also have to be times 2. So how much faster? It would be doubled. Okay? Because it is directly, there's no power. Whatever happens on the right needs to happen on the left. These 2 cases are very different. Please make sure you justify them in your mind. We'll do a lot of examples for practice, and we'll come to class to talk about any issues. Good luck!